Hello, today I am presenting you with an interesting math puzzle or problem where the context is an ant of negligible size sits on one end of a rubber band measuring 1 meter long. The ant crawls towards the other end of the band at a rate of 1 centimeter per second. At the same time, the band is being stretched uniformly at a rate of 1 meter per second, or 100 times faster in the same direction. Assuming the band can stretch to infinity, does the ant ever make it to the end of the band? And the answer is yes, and we can even calculate how long it will take. And spoiler alert, it will take a very long time for this poor little ant to get to the end. Okay, so to understand why the ant does eventually reach the end, you first have to make an observation that the band is being stretched uniformly. That's really the key part here. So in other words, if the ant at position 0 was in the middle instead of the beginning of the band, well, you can imagine 1 second later the band has stretched, but the area behind the ant, the 50% of the band behind the ant, gets stretched an equal amount to the 50% of the band in front of it. And each point along this band actually has a different velocity of stretching proportional to the position on the band. So in the beginning, this is the anchor. This never moves. This moves at a rate of 0 meters per second, or stretches at a rate of 0 meters per second. On the other end of the band, the end that we're trying to get to, our goal, it's being stretched at a rate of 1 meters per second, right? 1 second later, we're at 2 meters, and then the next second we're at 3 meters, and so on and so on. But what about the middle? Well, you can see the middle, it doesn't quite get stretched out the full meter per second, but it's definitely more than the beginning at 0 meters per second. So you can imagine in this example here, we start off with 0 as our anchor, 1 meter as our goal, and we're sitting at 50% right in the middle, or at 0.5 meters or 50 centimeters. In the next second, the band has been stretched to 2 meters. So now we have an anchor of 0 still, the other end is at 2 meters, but without the ant moving one single step, the ant actually gets pulled along to 1 meter. So we're still at 50%. It moved, however, 0.5 meters ahead, or 50% of the total velocity. The same thing at about a quarter of the way through the band. Well, that's going to be moving at 2.5. That's going to be moving at approximately 0.25 meters per second. At 3/4 of the way, it's going to be moving at approximately 0.5 meters per second. And again, at the very end, we're moving at 1 meter per second. So we go from 1 to 2 to 3, etc., etc. So the percentage of the band complete maintains the same point from second to second. Not the same point, it maintains the same middle point. So the ant gets stretched along, and at every second he'll stay at 50%. So now you can imagine, well, if the ant is moving on top of that, well, what is the percentage complete of the band at any given second? Well, you can see the percentage complete is just, it starts off with the ant is 0 centimeters, and this is the band length here. This is our starting position, start, right? When we start, the ant starts at the very beginning of the band at 0 centimeters, and it has 100 centimeters to go, so it has completed 0% of the band. Oops, let me pull down here. Well, what about at the next second? Well, at the next second, the ant has now moved 1 centimeter. But what percentage is that of the total band? Well, the total band length is now 200 centimeters. It has moved 1 meter. So the end is now at position 200 centimeters, but we have moved 1 centimeter. So we maintain that, and then the next second, we are going to move another centimeter. The ant is moving 1 centimeter per second relative to the band. But the band is now 300 centimeters long. And at the next second, again, the ant moves an additional 1 centimeter. And now the band is 400 centimeters. And this will continue on and on and on. Okay. So let's rewrite this or simplify it. So percent complete is going to equal, well, we can factor out a 1 over 100 centimeters. If I do 1 over, this is centimeters, 1 centimeter over 100 centimeters, and then we get, well, we get 0 over 1 plus 1 over 2 plus 1 over 3 plus 1 over 4 plus dot 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 plus 1 over t. Okay. Well, this portion here is what we call a partial harmonic series. And it is mathematically proven that this does not converge on any number. It actually will keep increasing to infinity. It will keep increasing to infinity and beyond. And a simple little proof to yourself, is the following. So imagine here's my harmonic series right here. Harmonic. And it's actually a partial because a harmonic series starts with 1, but in this case we're starting with 1/2. So we have a partial harmonic series. We have 1/2 plus 1/3 plus 1/4 and dot 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 dot. Well, imagine for a moment that we rewrite this, but we only use powers of 2. So we have 1/2 and then 1/3 gets replaced with 1/4. And then we have 1/4 and then 1/4 gets replaced with 1/8. And this keeps at 1/8. And then it keeps on 1/8 and then it goes to 1/16. Well, oops. Okay. I'll change my color back to white here. So we have 1/2 here. Well, these two things can be grouped as 1/2. These 4 things can be grouped as 1/2. And then the next 8 terms we can change to 1 over 16, which will again, we can combine to 1/2. And it goes on and on and on. So you can see the way I've written it here, we keep adding 1/2 and this keeps increasing. But to get to the next 1/2, we have to have more and more terms, right? We need only 1 1/2, we need 2 1/4, then we need 4 1/8, then we need 8 1/16, and then we need 16 32nds, and so on. So it keeps increasing, but at a slower and slower rate. Okay, so if this increases to infinity and beyond, well, the term above it, our partial harmonic series, again, we can group these. Well, this is certainly less than the series beneath it. So you can see that the partial harmonic series is going to be bigger than the one below it. And if the one below it goes to infinity, then the partial harmonic series must go to infinity as well, since it is getting bigger and bigger. Okay. So we have just proven that the harmonic series gets bigger and bigger, which means if we want our percent covered, so I'll rewrite the equation, percent covered, and that's a function of time, and we've just shown that this is 1 over 100 over 0 over 1 plus 1 over 2 plus 1 over 3 plus 1 over 4 plus dot 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 plus 1 over t. Well, so, and we want that to equal 1, right? We want to get to 100%. This is made to end. 100% of the band covered. Okay, well, let's rewrite this as 1/2 plus 1/3 plus 1/4 plus dot 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 plus 1 over t is going to equal 100, right? We just multiplied by this 100 on the other side. Well, since this series we've proven can get infinitely large, we know there must exist some t where we get to 100. Oops. There we go. Oops. There we go. Partial harmonic series gets infinitely large so therefore there is some there we go, t value, some amount of seconds, some value of t such that the sum gets to 100. Okay, this is very roughly the proof that eventually the ant will get to the end. And again, the logic is the area behind the band is also being stretched. So as the ant maintains its position, and additionally it moves at a rate of 1 centimeter per second, so it's actually incrementally getting closer and closer to the end, but just at a decreasing rate. So that kind of answers the question of does the ant make it? And the answer is yes. But how long does it actually take? Well, it turns out there's a approximation formula that we can use where we can say percent complete of t, and this is equals natural logarithm of t plus this constant value plus 1 over 2 times t. And this constant is called the Euler-Mascheroni constant. Euler-Mascheroni constant. And it is approximately equal to 2.68. Oh, I'm sorry. Oops. It's approximately equal to. I have it here. It's approximately equal to 0.5772. Okay, so it turns out when to get to a value of 100, so what does t equal? Well, when we solve for t, I'm not going to go through all the steps here, but when we solve for t, we get t equals approximately equals 2.688 e to the 43, which is this is scientific notation when it's expanded out, times 10 e to the 43. So there's 43 zeros on this number, or 43 digits, I should say, approximately. To just give you an idea, that is approximately 4,027 times 10 to the 11th years. And just for reference, the Earth is approximately 10.453 times 10 to the 9th, which is billion, years old. So it will take the ant roughly 100 times longer than the Earth has existed to get to the end of rubber band, which is pretty remarkable considering when we started, the band was only 100 centimeters long, and the ant is traveling again at a rate of 1 centimeter per second relative to the band. Wow, that's a long time. Thank you so much for watching. Stay tuned for more videos.